This video tutorial is to deal with the question of making a network diagram from a work breakdown schedule in the context of project management. So to describe first of all what a work breakdown schedule is. A work breakdown schedule is usually a table that lists all the different tasks that have to be completed for an overall project to be complete. It lists what the estimated duration is of all those tasks, and it lists what the dependencies are of those tasks. So let's look at this one here in front of us. I've got a number of different activities, all labeled between A and H. I've got all of the different estimates of how long each of those different activities will take to complete. And I've got all of the different dependencies of those tasks. Now, what these dependencies mean is that if I list, for instance, in the case of task C here, any immediate predecessors, that means that I have to have these tasks A and B complete before I can start task C. Anywhere where I don't have any immediate predecessors, that means that that task can start as soon as the project has started. So I can see for task A, task B, and task D, I don't need to have any other tasks complete. As soon as I start the project, I can start those tasks. What this question 7a, is asking is to prepare a project network diagram, to calculate the scheduling times and total slack for each activity, and to list the critical paths, activities, and the project duration. So let's have a look at that. I'm going to switch over to a kind of a nice tool that will allow me to draw out my project diagram easily. And just for ease of use, I've taken a screen print of my work breakdown schedule and I've copied it in here at the top of this diagram. So the first thing that we have to do in any network diagram in project management is we put in a start node. This just shows that the project has started, and then after that we can start to put in any of these different tasks that I can start straight away as soon as the project has started. And by that I mean, in this particular work breakdown schedule, I mean task A because it doesn't have any predecessor, task B because it doesn't have any predecessor, and task D because it doesn't have any predecessor. So each of those different tasks can start immediately and can start simultaneously with one another. So I'm going to draw on the different tasks on this network diagram for A, B, and D. Now, at the end of this project diagram, I'm going to have all of the different tasks with the predecessors or interdependencies shown with arrows. For the moment, just for the first draft of when I'm laying out my project network diagram, so that it's nice and tidy, just for the moment I'm not going to draw in any different arrows. I'm just going to do a brief kind of layout first of all, and then I'll draw in the arrows once I'm happy with the layout and that I'm happy that it will look tidy. Looking at the next task that I want to put in here, the one that I skipped over there that does have dependencies is task C, and I can see that C is dependent on A and B to be finished before it can start. So I'm going to put the task C somewhere over here so that I can draw arrows easily from A and B into C to show the dependencies. The next task that I'll be interested in is task E. So E is dependent on the task C. So again, I'm going to put E past C somewhere over here. And I'll just move that into position. Next task I'm interested in is task F. Task F is dependent on task D. So again, I'm going to insert the task F and move it down beside task D. Next task that I'm interested in is task G, and it is dependent on E and F. So I'm going to insert task G and move it over slightly over here so I can easily draw arrows between E and F to G. And then lastly, I've got task H. Task H, insert, and I'll put that past task G so I can easily draw an arrow in here. And my network diagram is taking shape. Now I need to put in all the different arrows to show all these different dependencies, and really I could have done that while I was doing all of those different tasks and done them both together, but I often do it this way so that I can make sure that I try and avoid any arrows crossing over one another. So let me change to my arrow tool and I will start drawing arrows between start and A, start and B, start and D. and then I need an arrow between A and B leading into C, and going down to E is dependent on C, so I need an arrow from C to E, and F is dependent on D. D has to finish before F can start, so I'll put an arrow between them. G is dependent on E and F, so I need to finish E and F before G can start. And then H is dependent on G, so I'll put an arrow between those two there. And let me just select all my arrows. I'll make them a slight bit thicker. Great. So that's a nice tidy network diagram. It clearly shows all the tasks, and it clearly shows all the interdependencies as well. It shows a definite flow from the start of the project, which tasks come first, and then as it moves through all the different interdependencies, it moves to a final point, which is in task H. At this stage, I want to start looking at the different scheduling times and total slack of each activity, and it involves a particular method, numerical method, which is quite involved. Before I go on to that, just to make it easier for me to quickly access the different estimated durations of all the different tasks, I'm going to put in a little subscript at the bottom of each of these different tasks that shows the estimated duration of each of them. And looking at my work breakdown schedule table, A has an estimated duration of 4, B has an estimated duration of 3, D has an estimated duration of 1, C has an estimated duration of 5, E also has an estimated duration of 5, F has an estimated duration of 2, G has an estimated duration of 5, and H has an estimated duration of 6. Now we're ready to go ahead and attempt this numerical method of finding all the different scheduling times and total slack of each activity, which I'll explain later. At the moment, from my work breakdown schedule, all of this information here is now contained in my chart. So I don't need this table anymore. It will give me more room. I can move my diagram up a little bit. And we can go ahead now and deduce the different scheduling times of each of the different tasks. So to allow me to do this, what I'm going to do is I'm going to draw on a crosshairs beside each of the different tasks. And as best as I can, I'm going to try and fit them in beside the different tasks. I usually go for the top right hand side of each of the tasks, and you usually try and keep it consistent. We might need a little bit more space there. I'll just move some of these paths down here, and I'll just give B a little bit more room so I can clearly see that crosshair here. So all of my different tasks, they've all got a crosshair just to the top right of them. Now what these crosshairs are for, well, I'm going to put in a different number in each of the different quadrants of these crosshairs, and then finally, once I've done that, I can calculate a different number for total slack, which I'll put at the top. To show what each of these different numbers mean, I'm going to put a legend over here at the top right of my diagram. And the first text for the first quadrant, what that is I'm going to put in there is ES, standing for early start, meaning what is the earliest possible start I can start an activity. The next number, which is in the top right quadrant, is EF, standing for early finish. What's the earliest possible time I can finish an activity? For the moment, I'm just going to leave it at those two, because I just need to calculate those two numbers for the first pass going from left to right across my network diagram. So let's apply that logic to some of these different tasks. If I look at task A, it can start immediately, as soon as the project can start. So the earliest possible time I can start task A is at day 0. So that's the number I'm going to put in here on this quadrant, the earliest possible start. Because A, the estimated duration is 4 days, if I can start the task at time 0, the earliest possible time I can finish that task is on day 4. So the number that I'm going to put in here for early finish is 4. Applying that logic that I'm just after doing there with task A to task B and task D, both of these tasks can also start as soon as the project starts. So each of them can start at day 0. So the early start of B and D is time 0. So I'll put 0 in each one of those quadrants. And then for task B, because it can start on day 0 and it takes 3 days, then the earliest possible time I can finish task B is on day 3. So I'll put 3 into that quadrant. And for task D, the earliest possible time I can start task D is day 0. So the earliest possible time I can finish task D, given that it's got an estimated duration of 1, is day 1. And 1 goes into that quadrant. Now, those earliest tasks, all of those tasks that can start simultaneously as soon as the project starts, they're quite easy to find out what the early start and the early finish are. Let's move on to some of the more kind of complicated tasks. For instance, task C. I want to fill in a number for this top left quadrant, the early start of task C. So again, I'm going to ask the question, what is the earliest possible time I can start task C? Now this is more tricky than what we've done with task A, B, and D before, because C is dependent on both A and B to be finished before task C can start. I have to have A and B finished and completed before I can start task C. So if I look at the different finishing times of task A and task B finishes on day 3, and the earliest possible time that task A can finish is day 4. So for me to be able to start task C, I have to wait for both B and A to be finished, and therefore I'm going to take that number from the early finish of A, and that is a number that I'm going to be putting in this early start of C. The earliest possible time I can start C is when A is finished at day 4. So I take the 4 from that quadrant and I place the 4 here. Given that task C has an estimated duration of 5 days and the earliest possible time I can start task C is on day 4, then the earliest possible time I can finish task C is 4 plus 5, which is day 9. Let's look at task F. Task F is dependent on task D to be finished before it can start. So the earliest possible finish for task D is the day 1. So therefore the earliest possible time I can start task F is day 1. Given that F has a duration of 2, the earliest possible time I can finish task F is 1 plus 2 is 3. Let's look at task E. Task E is dependent on C to finish. Therefore, the earliest possible time I can start E is when C finishes on day 9. So that's the number that I'm going to put in on the early start quadrant of E. And given that E takes 5 days, the earliest possible time I can finish task E is 9 plus 5, which is day 14. Let's move down to task G. Now again, G is a little bit more complicated than E or F because I've got 2 different dependencies there. G is dependent on E and F to be finished before it can start. So I have a choice here of whether I take the 14 or the 3. So it was similar to the choice that I made back with task C when I had to choose the early finish times of A or B as the early start time of C. And the logic again holds. I have to hold off and wait for both of these tasks to finish before I can start task G. So if F has an early finish of 3 and E has an early finish of 14, I have to wait for E at day 14. So on the way over in this forward pass, I always take the highest number of the early start quadrants of the preceding tasks. The early start of G is 14. The earliest possible finish time is 14 plus 5, which is 19. And then I've got task H is the only one left. And again, that's a lot more straightforward. I've just got one dependency there. So the earliest possible start time is day 19. And the earliest possible finish time is 19 plus 6, 25. Having done the first pass across my project network diagram, looking at all the early starts and early finishes of all the different tasks, I've come up with this early finish number, which is of task H. Now task H is the last task. All the other tasks are feeding into it. Therefore, whatever this earliest finish time or number is for task H, that is the overall duration of the entire project. This entire project, the way that it's scheduled at the moment, it takes 25 days to complete all the different tasks, to complete the entire project. And I'll just take note of that down here in the bottom right of my diagram. I've mentioned a few times that all of these numbers that we've done for the early start and early finish quadrants of my crosshairs on all the different tasks, that it's the first pass going from left to right across my diagram. Now we're at a stage when we can do the second pass, which is backwards, right to left across the diagram. And before I do that, I need to fill in what the different quadrants at the bottom of my crosshair stand for. The bottom left-hand quadrant of the crosshairs, it stands for late start. What's the latest possible time I can start this task, but still keep the overall project on track to finish in 25 days? And the bottom right-hand quadrant of my crosshairs is late finish. Again, what's the latest possible time I can finish this task, but still keep the overall project duration on track? Now we'll understand this late start and late finish concept as we work backwards through the tasks. So first of all, let's go for the last task, which is task H. What's the latest possible time I can finish task H, but still keep the overall project duration at 25 days? Well, at this last task is very, very simple. I have to finish it by 25 days if I want to finish it by 25 days. So always, if I've got this kind of scenario where I've got converging tasks coming into one particular task at the end of the project, the numbers at the top of the crosshairs always are the same as the numbers at the bottom. So the latest possible time I can finish task H is at day 25 and still keep the overall project duration on track to finish in day 25. And because H takes 6 days, 25 minus 6 is equal to 19. That means that's the latest possible time that I can afford to let H start and still keep the overall project schedule on track. Let's look at task G. Again, I'm going to fill in the late finish quadrant first of all. What's the latest possible time I can finish task G and still keep the overall project duration on track to finish in 25 days? Well, I have to allow task H to start at day 19. So the latest possible time I can finish task G and still keep the whole project schedule on track is at day 19. I have to get finished by that time to allow H to finish. So I'm going to copy that text box from here. I'm going to take that 19 from there and put it there as the late finish in task G. Because G takes 5 days to complete, the latest possible time I can start task G and still keep the overall project schedule on track is at day 14. That's 19 minus 5. Let's look at the late finish for task E. What's the latest possible time I can finish task E and still keep the overall project duration on schedule? Again, I have to get E finished by day 14 to allow G to start by day 14 and keep all the tracks on schedule. So I am going to take the 14 from here and put it into this quadrant here. Task E takes 5 days. So 14 minus 5 is 9. 9 is the latest possible I can start task E and still keep the overall project duration on schedule. Let's look at task F. What's the latest possible time I can finish task F and still keep the overall project duration on schedule? Well, to allow G to start by day 14, I have to get task F finished by day 14. It doesn't matter so much that E and F could possibly finish on the same day, as long as they're both finished in time for G to start at day 14. that's fine. So I'm going to take the late start of G and I'm going to use it as the late finish of F. Because the duration of F is 2, 14 minus 2 is 12. When looking at task C, what's the latest possible time I can finish task C and still keep the overall project duration on schedule? Well, I have to get it finished by day 9 to allow E to start at day 9. So day 9 is the late finish of C. And 9 minus 5 is 4. Let's look at task D. D down here, to allow F to start at day 12, I am going to make sure that D is finished by day 12 as well. So you can see a pattern emerging here as well. I keep on looking at the following task from the task that I'm dealing with at the moment, and I pick out the late start of that task, 12 of F in this case, and I use that as the late finish of the task that I'm dealing with. So 12. Late start for D is 12 minus 1 is 11. Now, looking at task B. Task B has to get finished by day 4 to allow C to start at day 4. So I'm going to take the 4 from there and I'm going to bring it back here for there. 4 minus 3 is 1. So the late start of B is 1. And then lastly, looking at task A, what's the latest possible time I can finish task A and still keep the overall project schedule on track? Well, the latest start of C is 4, so I'm going to take the 4 from there and I'm going to use it as the late finish of A. And 4 minus 4 is 0. And I'll move that into the late start position. And that finishes the second pass going from right to left across my network diagram. Now, the final piece of what happens to this legend over here is a number that I'm going to put right up at the top of each crosshair. In the legend, I'm going to put in the abbreviation TS, standing for total slack or total slippage. For the moment, I'm not going to explain what total slippage is. It will become clearer when we go on to the critical path method. But it's enough to say how to calculate the total slippage is I just take the late finish and subtract from it the early finish number of each of the different activities. So let me write that formula down. If I apply that formula to each of the different activities, these are the numbers that I get. For activity H, 25 minus 25 equals 0. For activity G, 19 minus 19 equals 0. For activity E, 14 minus 14 equals 0. For activity F, 14 minus 3 equals 11. For activity D, 12 minus 1 is equal to 11. For activity C, 9 minus 9 equals 0. For activity A, 4 minus 4 equals 0. And lastly, for activity B, 4 minus 3 equals 1. So those are all the total slacks or total slippages for the different activities in this project network diagram. At this stage, no matter what project network diagram that we're looking at, there will always be at least one path going from the start to the finishing task that has a trail of zeros on it. Now I say at least one because you can have more than one path, but in this project network diagram I just have the one. Going from the start, I see task A, task C, task E, task G and task H all have zeros for their total slippage. This path in any project network diagram is known as the critical path. And I'm just going to take a note of what the critical path is here. What the critical path means is that these tasks have to be finished on time as regards their estimated duration for the overall project to remain on schedule. If there is any slippage or if there is any in the completion of these tasks, the overall project duration of 25 days will slip. Having zero slippage means that there is no leeway. On the other hand, these tasks that aren't on the critical path, B, D, and F, they have a certain amount of slippage. They have a certain amount of leeway. So for instance, with task F, I have 11 days slippage, which is quite generous, meaning that as a project manager, I don't have to be overly worried about the overall project schedule if task F starts to slip or starts to take a little bit longer than its expected 2 days. It's the same with task D and task B, although task B only has 1 day slippage. If task B goes from 3 days to 4 days, it's not anything to panic about. But if it goes any more than that, then all of a sudden it will have an effect on the overall project duration. So going through the steps that we have seen in this video tutorial, we have created a project network diagram. We've calculated the scheduling times and the total slack for each activity. We've calculated the overall project duration. And we've deduced it from all of that what the critical path of this particular project is. This is all really useful information for project managers. And this should be kept on hand for measuring the project's progress. The overall label that I'll put on this whole procedure is known as Work Breakdown Schedule to Project Network Diagram and the Critical Path Method.